Beryllium is what hybridization? SP. So I mentioned that I want to see the lone pairs on fluorine. Some people had it missing. The reason I need to see the lone pairs on fluorine is to tell me what the fluorine is hybridized. What is the hybridization on fluorine? sp3. And this one? sp3, because it's got 3 lone pairs and 1 bond. 3 lone pairs and 1 bond is 4 groups. Now we're going to have 3 energy level diagrams. The 3 energy level diagrams, and here we have to color code. And so I might as well talk about this now. The 3 energy levels, of course, we have beryllium. 50% S, 50% P. 1 part S, 1 part P. And so what we do is we have 2 sp orbitals. And how many p orbitals? Unhybridized. 2. There's a beryllium. And from beryllium's perspective, how many electrons does beryllium have in this structure? It has 2 electrons. 1. Should I pair it? No, it looks like it has 2 bonds, so this looks right. Right? 1, 2. What about these p orbitals? These p orbitals are what we call empty. Now, this is less than an octet. Unfortunately, it'd be great if we could get an octet, which is 8 electrons, but we can't. We're going to have to live with less than an octet because what we're going to have is we're going to have fluorine. Fluorine's going to come in with what orbital? A fluorine sp3 is going to come in. This is beryllium sp. And bond here. The fluorine sp3 is going to bond here. And so this is what I mean. If you use the same color, then code it differently, like this, so we know electrons are different, from different origin. Or you use another fluorine sp3 is going to come in. We have to write both of them, because if you just write one fluorine, it looks like it double bonds, you know. So we write both of them in there like that. Now, we have to also look at it from the point of view of fluorine. Both of the fluorines are the same, so I don't necessarily have to draw 2 energy level diagrams. Since both of them look the same, I'll just draw one. What is the hybridization on it? sp3. How many sp3 orbitals are there? 2? Is that right? Is it 2? Double check that. How many is it? 4. Yeah, Jeanette, right. It's 4. sp3, 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 4. How many electrons does fluorine have? 7. And so let's fill this up. 1, 2. I'm going to fill it blue. Oops. How did I pair? You know, I automatically see how many lone pairs are there? 3 and 1 bond. So I was automatically going to fill it the quickest way, but I'm not. 1, 2, 3, 4, 5, 6, 7. 3 lone pairs and 1 bond. But this cannot be spin up. Why can't this be spin up? Because if beryllium is spin up, then fluorine must be spin down. So I need to flip the spin here to spin down. Because what's going to happen is beryllium is going to come in with its sp orbital here and bond, spin up. And so we have 2 of these, so times 2. This is fluorine sp3. And so when I draw this, I just, you know, memorize each of them and draw it the same way each time. And so we have 1 electron in this sp, 1 electron. The sp orbitals are oriented 180 apart from each other. Then we got a fluorine coming in. Now, how do you draw a tetrahedral? We always draw it the same way. We have 1 in the plane. So this would be like the top one. And then we'll have 1 at a 109, also in the plane. And that means we got to have 1 sticking out of the plane. And then 1 going in. Do you see? So what I did was I just twisted the tetrahedral on its side here and then have it like this. And then just fill it. I have three lone pairs and one single electron. These are the sp3 orbitals here. So this would be fluorine. This would be beryllium. And then we got another fluorine here. One in the plane. Excuse me. And then what I'm going to do is I'm going to flip it. So this one is in the plane. And so I'll take that one and rotate it 180. I get this. And then I get this one coming out. And then one coming in. Do you see it? And then again, we're going to have a bond, but what is this bond called? What is this bond called? Is it a sigma bond? Yeah, because if I drew a line connecting the two nuclei, the overlap is in that region. And so this is called an sp3 sp sigma bond. Or sp3, it doesn't matter. The ordering. Good? And then we could draw the cloud. You know, if we want to get all detailed in here, we know that fluorine is much more electronegative than beryllium. And so the electron cloud is going to be distorted towards fluorine. So this is going to be highly polar, this bond. And the same thing here, this electron cloud is going to be distorted towards fluorine. But even though we look at these two dipoles, so we have a dipole going out this way and dipole going out this way, they're equal and opposite. We have equal and opposite dipoles, it's going to cancel out, and we're going to call BEF2 polar or nonpolar. Even though it has polar bonds, BEF2 is nonpolar. Nonpolar. What's the shape? Well, it's linear. And the angle? There's only one angle, the FBEF angle. It's 180 degrees. And so we want the EG. What's the EG is linear. The MG is also linear. Let's see here. Okay, just to make this clearer, this should be dashed. Dashing so much. And I could have made this one a mirror of this, but I flipped it. Now, do you see how I flipped it? 180. The reason I flipped it is because I'm thinking about something called steric hindrance. Steric hindrance is we try to minimize repulsions. And so if I put this one up, then this orbital sees this orbital. I mean, it's kind of far away, but they're right aligned against each other. Do you see that? So what I did was I twisted one of them down so that they aren't looking straight at each other. In fact, do you see, if I twist this one down, this one's looking between these two orbitals, and this one's looking between these two orbitals, so we don't have the orbitals superimposed like that. So I twisted it a little bit. Do you see that? Well, that's the reason I drew it like this, because we want to minimize, all the repulsions. So I'm thinking about that as well. Well, we're out of time, unfortunately, so we'll continue on Thursday.